Thank you. Just share my screen. Okay, can you see my screen?
We're good to go.
Great. Thank you. So today we are going to talk about galaxies, and there are a lot of them. And I'm trying to. Okay. So if you see a deep sky image like this, which this one is Hubble's deepest image, you can see it's filled with galaxies of different sizes, colors, and shapes. You can see some red ones, you can see some blue spirals, and you can see some interacting galaxies. And so all these galaxies have different shapes and sizes and colors, basically. And the study of galaxy formation and evolution focuses on how this galaxy is formed and how they change or evolve with time as we look through the different epochs of the universe. And so let's step back and start from the beginning, how it all started. So in 1920s, Edwin Hubble made a couple of discoveries, which I think started the field of extragalactic astronomy. The first one is he looked at an object which and measured the distance and thought that this was very far. And he estimated that this object was about 7 or 8 times further than the furthest known star in our own galaxy. And so he said that, okay, this cannot be the object in our own galaxy. It should be outside our own galaxy. And it turns out correct. He was looking at the Andromeda galaxy. And so that's how the people started looking at the galaxies outside our own Milky Way. The second thing Edwin Hubble did was he looked at number of galaxies outside our own Milky Way and saw that as the distance to the galaxy increased, the speed at which it was going away from us also increased. And so you can see here, this is a more recent plot. Hubble didn't have this many points at that time, or not observations were this many. But the idea is that as the distance increases to a given galaxy, the velocity at which it moves away from us increases. And that's a nice linear relation, which initially was called the Hubble law, and now it's called Hubble-Lemaitre law. And so what it's saying that the universe is expanding. As we look outside, everything is going away from us. And it's something like you see in the raisin bread dough at the bottom here. The galaxies or the spots on that dough, they remain the same. The size remains the same, but the dough itself rises after a few hours. And so what is happening here is the space between the galaxies expanding. The galaxies remains there, the shape, size remains the same, but the space between the galaxies is expanding. And that's how the expansion of the universe or expanding universe came about. And these two discoveries from Hubble were key to start the extragalactic astronomy field. Now, one consequence of expanding universe is that as the light travels to this expanding universe, the light is also stretched into longer wavelengths. And this is called the cosmological redshift. You will, in this presentation, I will mention a lot of times the redshift, which in some sense is indicating how far the galaxy is from us. And so the light, if it's emitted by a galaxy in the ultraviolet wavelength, then it is stretched to longer wavelength as it comes to us. So as you can see in the electromagnetic spectrum here, the ultraviolet and the longer wavelength means you are going towards visible and infrared wavelengths here. And so depending on the distance, how far the galaxy is, if the galaxy emits ultraviolet and if it's further away, you will see in the visible. If it's very far away, then you will see actually in the infrared. And so I have shown here some example redshifts. So if you're looking at redshift 0, basically you're looking at the right now, the time now. And so it's basically about 13.7 gigayears times time since the Big Bang. If it's, I would call redshift 1, it's about 6 gigayears from the Big Bang, or the light has taken about 7.7 gigayears to come to us. And so as the redshift increases, you are going more towards the Big Bang. You're closer to the Big Bang. So when I talk about redshift 9, 10 galaxies, you are looking at the first 500 million years from the Big Bang. So very beginning of the universe, early universe. And so expansion of universe as discovered by Hubble basically also says that if universe is expanding, in the past it has started at some point, at a singular point. And that's what we now call the Big Bang. That's where we predict that the universe has started. It was a very hot in the initial phase, but it started expanding and it started cooling. And in one phase, about 400,000 years after the Big Bang, there was a time when you start to see this small structure in the universe, in the background. And the light which was emitted at 400,000 years after the Big Bang has reached us, has redshifted, and we see that light in the microwave. And I'm showing here, it's called the cosmic microwave background. And I see here that we have experiments from COBE, WMAP, and Planck in different years. And you see we have improved on the resolution as with every mission. COBE was not very clearly resolved. WMAP was a little better. Planck is much, much better. And this cosmic microwave background is showing you the differences in the temperature and the density in the universe at that time, 400,000 years after the Big Bang. But the differences are very, very small, 1 in 100,000 parts. But this is where the universe started forming structures. And the other thing is that what is universe made of? If you can see here, it's 69% is dark energy, 26% is dark matter, and only 5% is a normal matter. The normal matter is what we see. Stars, galaxies, what we are made of. All this is just 5%, all the elements of periodic table. The dark matter, the 26%, is that those are made up of particles which don't interact with light. And so we cannot see. That's why it's dark. But we see that their presence because of the gravity and other aspects. And 69% is the dark energy. It's basically a vacuum pressure, which is what is driving the expansion. Because what we expect from the gravity is that by gravity, everything should come close or come together. But the dark energy is repelling force, and it's basically expanding the universe. These are the key aspects of galaxies you will see as we go along. And so how galaxies start forming in early universe? What are the first galaxies? Now, the formation process of first galaxies, first stars, and even first black holes is highly uncertain because we haven't observed that epoch and the time, which is very early in the universe. It started probably around 200 million years after the Big Bang. And so what we need is simulations to predict how galaxy must have started forming. And there are a few scenarios here. I have shown here a couple of them. One is the hierarchical structure from smaller clumps, as I have shown here in the cosmic microwave background. Those start to grow. Basically, those overdensities start to grow through the gravity. They come close together. They form bigger clumps. They collapse, and they form stars, globular clusters. And depending on the property of the cloud, you will form disk galaxies, and then those galaxies merge, and you form massive galaxies like this one at the end, which is the elliptical galaxy. And here also another cartoon shows that the smaller galaxies merge and they form the bigger galaxies. That's one scenario. But when we look at the observations, we see massive galaxies very similar to the elliptical galaxies in very early universe. And so we don't know how they must have formed because the process here, the hierarchy formation, takes millions, billions years to form this galaxy. But we already see some of these galaxies in first few 100 million years. And so there is another possibility that maybe there is a formation scenario called monolithic collapse, where a big cloud just collapses to form the first galaxies based on their angular momentum or density. And it's possible that in reality, the galaxy forms as a combination of all these processes, or one process dominates the other, but we don't know. And probably James Webb will be able to get some idea about that as we look deep into the sky. But in general, galaxies are a collection of stars, gas, dust, and dark matter held together by the gravity. And so since Hubble, lots of ground-based telescopes have come out, from 2-meter, which Hubble used to observe 100-inch, to all the way to the Keck telescope, which is 10-meter, then 8-meter class telescopes from VLT, all the way to the Apache Point Observatory, which is a 2.5-meter telescope. And it has been used for a Sloan digital sky survey, which is basically scanning the sky looking at nearby galaxies and covering a lot of skies, because this large telescopes look at a very small region of the sky, but smaller telescopes can scan a pretty big chunk of sky, and those are great for doing survey type science. And so from ground-based, since Hubble all the way to 1990s, couple of results I would like to mention, which has come practically from the ground-based observations. The first one is that Hubble, when he was observing all the galaxies, nearby galaxies in 1920s and 30s, started to see that the galaxies are of different shapes and even sizes in some. And so he started to classify those galaxies. And he started to make what is called a tuning fork, or the Hubble sequence, where you can see different types of elliptical galaxies, and then you have different kinds of spiral galaxies, depending on whether the spiral galaxies have bars or not. And so he started classifying those in 1930s. And Dweckler in 1950s and 60s did more detailed observations of this nearby galaxies and did a finer classification of galaxies, depending on how tight the spiral arms were, all the way to irregular galaxies, which Hubble didn't point it out in this scheme earlier. Now, these different types of galaxies are not just giving you the shapes and size, but they have properties. Like elliptical galaxies usually contain old stars. There are no active star formation going on in these galaxies. They look red. Spirals are usually star-forming galaxies. They have a combination of young and old stars, and they're usually blue with some red center. And irregular galaxies are more starburst, young stars, and they are usually blue, and they have little dust. Now, what we are seeing now is, as we look at the different time in the universe, we don't see the same structure in the galaxies. And as you can see here in this plot, the nearby galaxies, which Hubble and Dweckler saw, they were very nice spiral galaxies. You can see, or nice elliptical galaxies. But as you go further in time, you see that the galaxy shapes are not same. The sizes have become small. And so what it's saying that over time, the galaxies have grown, merged, and become what we see today now. Because as you can see, in early times, they were practically like dots. Then you see some of the mergers were happening, and then you start to see the bigger galaxies that we see now. And so that's how the galaxy has evolved, we think. But we try to see the galaxies at the different time in the universe and try to infer what has happened, what are the properties of the galaxies, and what's going on as they evolve with time. And the second result that has come out of the ground-based observation is what's called the large-scale structure. Now, Sloan's Digital Sky Survey and other ground-based 2-4 meter telescopes have looked at thousands of galaxies in the sky. And what we are showing here is a distribution of galaxies in the sky. And they have measured redshift, so we know where they are as far as the distance is concerned. And you can see that if you look at the bigger picture, the galaxies are not uniformly distributed in the space. You see they are clustered, you see there are filaments, you see there are voids where there are no galaxies, and there are all kinds of structure going on. There are superclusters where dense, a lot of galaxies are there. Then there are voids, there are no galaxies, and then there are various kinds of structures you can see here. Same is with the other survey. This was Sloan's survey, this is the other survey, and you can see that there are different kinds of structure in the universe. And these two panels on the right and on the bottom are the simulations. These are the theoretical models which have reproduced the observed large-scale structures. And you can see this and this, the left and right are pretty similar. And the bottom one and the top one also are quite similar. Now, the similarities between the observations and the simulations, or theoretical and observations, puts a strong concern on cosmological models, because the models which generate the simulations, if they match with observations, then you can say a lot about the models and what are the physical processes going on here. But as far as the galaxy evolution is concerned, the galaxy properties and how they change with time strongly depends on where they reside. So if the galaxy is in the cluster, it will evolve differently. If its galaxy resides in one of the low density regions, then it will evolve differently. And so the ground-based telescopes have done excellent work in doing all these kinds of surveys. And they're excellent resource to do extragalactic studies. Even today, these large telescopes have been excellent in doing these studies, but they are limited by the intervening atmosphere, because atmosphere doesn't allow the clear view of distant galaxies, and also they don't allow some of the wavelengths or some of the light to come to us on the ground. So atmosphere blocks certain wavelengths, like near infrared or ultraviolet, you cannot see from the ground. And so in 1990, Hubble was launched, as we all know. It's a 2.4 meter, it's a small telescope, but it's above the atmosphere. So it doesn't affect the atmospheric effects. And so it sees both clear images and it detects the wavelengths that Earth atmosphere usually blocks. And so now you can see much further than what you can see from the ground. And so here I can show you that from the ground-based observatories, we have seen up to redshift 1, which is 6 billion years from the Big Bang, so about halfway in the universe. And with the various surveys in the Hubble, we have gone all the way to about 500 million years or 600 million years before the Big Bang. So we have gone very close to the early universe phase of the universe. And with the clearer images, as you can see on the rightmost panel here, the ground-based images on the top and the Hubble on the bottom, you can see that Hubble gives much clearer image, and that's because it's in this space. Hubble has been repaired and serviced for a few times, and so the instruments in the Hubbles have changed. Currently, there are 4 instruments: STIS, COS, ACS, and WIFIC-3. Those are working on the Hubble, and they observe in ultraviolet, visible, and near-infrared wavelengths. Now, the Hubble really started looking at the galaxy evolution study with the Hubble Deep Field. In 1995, some astronomers decided that let's point Hubble for a long period of time on a blank piece of sky. Blank, as we knew from the ground-based data at that time, and say that it looks pretty blank, and we just spend a few days of Hubble's time and looking at that patch of sky. It's a very small area of the sky. And they were surprised when the observations came, because not only it was not blank, it contained many galaxies of different shapes and sizes. And so the universe was just filled with all these galaxies. And so this is the first time Hubble discovered distant galaxies going all the way to redshift 4, which was basically 2 giga-years after the Big Bang. And a lot of other things were come out of the Hubble Deep Field. We were able to do multi-wavelength photometry, so you can imagine different filters. And then based on those, you can estimate redshifts, which are called photometric redshifts, just based on images. So that was a new with the Hubble Deep Field. Again, with the Hubble Deep Field, you saw that the galaxies have different sizes and shapes as a function of time. The star formation properties of the galaxies were different compared to what we see in the nearby universe and the distant universe. And the main thing was that it basically changed the culture. Until 1995, people were reluctant in the sense to do large programs, deep observations with Hubble. And with Hubble Deep Field, everything basically changed. And the focus turned to doing large, deep surveys with Hubble to do galaxy evolution studies. And so this is a very small sample of some of the large programs that Hubble has done. As I have put a disclaimer up there, this is highly biased and incomplete list because it's only lists some specific programs. But the idea is to show that there's lots and lots of programs Hubble have done, which are focused on galaxies and galaxy evolution. And as you can see here, the orbits, one orbit typically takes about 1 hour. And so the programs here are shown, they go for 400 hours all the way to 400, 600 hours, 900 hours. So these are like days. The programs which Hubble takes observations for like 30 days, 40 days. And so these are pretty large programs trying to look at distant galaxies, trying to understand the properties of the distant galaxies. And obviously, there are many other smaller programs which are focused on some very smaller parts of the sky, looked at this smaller sample of galaxies. But these are some of the largest programs of the Hubble. And just to give some idea here, in 2002, Hubble had a new camera called Advanced Camera for Surveys, ACS. And within ACS has a field of view, which is this small. This is Hubble Ultra Deep Field, is 1 ACS pointing. And it is just a fraction of the full moon. It's a very small field. And so Hubble Ultra Deep Field is the deepest field HST has observed. But then different size fields are observed, like GOODS was bigger than Hubble Ultra Deep Field, the GEMS was bigger than that. And the Cosmos here is about 2 square degrees, which is much bigger than the full moon. And all these programs and the targets in these galaxies have continually frequently been used as a targets for multi-wavelength studies with different telescopes from ALMA to near-Earth observations from Wide Field Camera 3 to JWST, and even from the ground with Keck and other telescopes. And so as an example, I have shown here that this is a redshift 2.3 galaxy shown in the GOODS field. And as you can see, it's a pretty compact galaxy, which shows red because we are seeing it in the redder wavelengths. And so about 1,500 orbits in this program, so 1,500 hours of HST time has gone into some of these programs. One of the programs, large program, has looked specifically at Andromeda because this is the nearest large galaxy we have. And you can see here the picture in comparison to the full moon. It's pretty huge in the sky, the Andromeda galaxy. And a small portion of Andromeda, about 1/3 of Andromeda, was observed by HST using 6 filters. But it took about 40 days, and I would say about 800 orbits to a small patch of Andromeda galaxy. And on the right, I show you a very, very tiny portion of this mosaic from HST, and you can see how many stars are there in that small region of the sky. You have star clusters, you have different types of stars, red stars, blue stars, and there are millions of stars. And this particular program was able to do extensive study about 100 million stars in Andromeda, 2,500 star clusters. And so by looking at this nearby galaxy like Andromeda, you can do extensive detailed study of stellar evolution, how stars evolve, what is the star formation process going on in this type of galaxies, and various other properties of the galaxy in detail. And even when you're looking at this nearby galaxy, you have background sources, and so you can also study background sources with this kind of deep observations. One other program, which was the CANDLES program from Hubble, which was done over 3 years again, but this was looking at the distant galaxies, and it did observations over 5 different fields in the sky, and it was about 900 orbits, and it used HST's near-infrared bands and ACS visible bands, and looked at about 250,000 galaxies, distant galaxies. And these galaxies will have redshifts starting from about 1 to 8. So you're looking at about few 100 million years after the Big Bang, all the way to about 6 or 7 billion years after the Big Bang. So you have a huge amount of cosmic time to look at through this observations. One result I have shown here is the supernova. The supernovas are basically the exploding stars, and mostly they are observed in the nearby galaxies, close by galaxies. But with such deep observations from CANDLES, you are able to observe supernova at redshift of 2, which is pretty far. And then in the bottom here, I show on the right bottom, you show different types of galaxies you can observe in such deep observations. And various studies have been done using this data by the team itself and the community. So it's a huge amount of investment from HST, and the community has taken advantage of that. And then instead of looking at the blank sky and trying to go deep, what other programs have done is they've looked at the nearby galaxy clusters. So these are the clusters which are at redshift 0.5, so pretty close. And what you're trying to do is use these clusters as gravitational lenses. And so the galaxies which are very further away, gets magnified because of this gravitational lenses or the clusters. And as you can see in the right panels here, the red galaxies which are magnified, which are way further than the cluster itself. But because they are magnified, you can now study those galaxies in detail. And those are some of the faintest galaxies Hubble has observed is through magnification, because now the galaxies are magnified many, many times. And so you can observe them and try to study them. And all this sample of galaxies which have been collected through these programs are again going through extensive follow-ups through various telescopes. And then there's a way to do called the archival deep fields, where people have taken all the observations of HST in last, say, 10 years in a single patch of sky. So this is Hubble Ultra Deep Field, taken with ultraviolet, visible, and near infrared. And all those data, is about 2,500 exposures, have been stacked to make this nice image here. And this is the deepest image from the Hubble, which goes equivalent to what JWST will do in the near infrared. And similarly, this is a very small patch of sky. This is a little bit larger, but again, 14 years of data has been compiled here and combined to make this big mosaic of combining about 7,000 exposures. And so now you can use this to do deep field observations, which we were not able to before. And so these are all the observations of the deep field. Now, what we do with these observations, how we study galaxies, because we need to identify these galaxies and to figure out how far they are. We need to know the redshifts. And so one way to do is, so I'm showing you here what's called the Lyman break selection technique. So these are the filters or the pass bands or the wavelengths which Hubble observes usually from the blue to near infrared. And these are the images taken of a one galaxy in those bands. And the gray here is spectral energy distribution of a star-forming galaxy, simple form, and it's about redshift 3. But now, as you can see here, as you go to further and further, this is now a redshift 5, you see that there is no light in the bluer bands. And you see the below here. So what is happening is that the blue light from this galaxy at redshift 5, when it passes through the neutral hydrogen between us and that galaxy, the blue light get absorbed and it never reaches us. And that's why we don't see anything in the bluer bands. And so what we do is when we observe these distant galaxies in 3 or 4 filters, then we can use the colors, the difference between this filter and this filter, and this filter and this filter, and try to estimate the redshift of this galaxies. And as you can see, as you go further and further, all the blue bands have no light, basically, and only the near infrared is visible, correct? So you are not going further and further. And so now you see this break, which we call the spectral break. And so if you have an observation at the top of the break and observation at the bottom of the break, then you can look at that difference and try to estimate the redshifts. And so what we do, so on the left panel, there's a lot of information here, but I'll go hopefully slowly here, is instead of looking at just 2 colors on the top of the break and the bottom of the break, what we now do is we take the multi-wavelength data. So we have a lot of data in different bands, and we try to fit with called spectral energy distribution models. Now, these models are based on the known galaxies in the nearby universe. And so these models are then redshifted, and we try to fit that to what we observe. And that's how we estimate the redshift of a galaxy. And this is called the photometric redshift. It's not very accurate, but we get the ballpark estimate of how far this galaxy is. Once we know how far these galaxies are, and this method you can do for thousands of galaxies, and that's the idea here, that when you look at these deep fields, which has thousands of galaxies, and you want to know the distance or the redshift of these galaxies, how you do, and this is the way to do it by just looking at the photometry or the colors of the galaxies. And the one thing, once you have redshifts, now you try to look at the statistical distribution of these galaxies. Say between a certain brightness, how many galaxies are there? So for each bin in the brightness, you basically count number of galaxies. Say so this is the faint end and this is the bright end. So you look at between -18, -19, how many galaxies are there, between -19, -20, how many galaxies are there. And that's how you get a luminosity function, or it's basically a UV luminosity function. And depending on the shape, evolution, and other parameters of this function, you can say something about the galaxy population, because on the faint end, these are the faint galaxies, and these are the bright end, these are the bright galaxies in that epoch of redshift. And then once you have a luminosity function, you integrate it and try to get something about star formation in the universe. And the plot here shows the star formation density as a function of time. Redshift is basically a time. And so you can see the star formation activity in galaxies was maximum around redshift 2 and 3. So it started building up at the beginning of the time. It started building up and it went to peak to the redshift 2 and 3, and now it's decreasing basically. But when you're talking about the star formation, when there's a lot of star formation, there is a lot of dust. And the dust can affect our estimation of the star formation. And so that's why we have two different colors shown here, which is one is corrected for dust and one is not corrected for dust. But this shows how star formation activity is going on in the universe in general as a function of time. The other thing, what we do is try to estimate the physical properties of these galaxies. And so we take all the spectral energy distribution we have, and we fit it, those models fit it to the photometry we have. And based on the fitting, we can estimate what the stellar mass of this galaxy, what are the star formation rates, what are the stellar ages. And so we can get some idea of the physical properties. And on the right here is shown that at higher redshifts, if we need to get the estimate for the dust, we look at the UV spectrum and try to look at the slope of the spectrum and estimate the dust. Because at the higher redshifts, we don't have that much infrared data. And so usually when you want to estimate the dust, you compare the UV light to the infrared light and try to estimate the dust. But as you go to higher and higher redshifts, the infrared has gone into far infrared, and we don't have that many observations for those galaxies. And so we have to estimate just based on the UV colors. So spectral energy distribution fitting is one way to get the physical properties of the higher redshift galaxies. And the other thing beyond physical properties, we look at the morphologies of the galaxies. And you see here, this is the same galaxy shown in the different passbands or different wavelengths. And so this is in the rest-frame of optical, and this is the rest-frame ultraviolet. And you see there are differences in the shapes and sizes, because that depends on what kind of stars there are in these galaxies. If there are UV stars, then they're bright in UV. But if they're not, then you don't see those UV lights. So depending on the wavelengths you're looking at, you will see different shape and size of the galaxies. And then you try to look at different types of galaxies as Hubble did, but now you're looking as a function of time, as a function of redshifts. You see that there are more spheroids nearby, but if you go to the higher redshifts, you see more irregular galaxies. Same is with the galaxy sizes. People have measured the galaxy sizes, and it seems that as you go to the higher and higher redshifts, further away, the galaxy sizes are becoming smaller. And the merging of galaxies, as I mentioned earlier, is a prime process where the galaxy grows. Basically, smaller galaxies merge to make bigger galaxies. And so people have tried to look at what is called the merger history or the merger rate in the universe as a function of time. But as you can see, there are a lot of uncertainties here. James Webb and hopefully future telescopes will try to minimize those uncertainties. And Hubble, along with spectroscopic observations from the ground, has enabled a range of science investigations. I'm not going into the details here, but you can do lots of excellent things with the spectroscopy, emission absorption line properties. You can look at the circumgalactic, intergalactic medium, so the gas around the galaxy and their properties. What's the gas flowing out, going into the galaxies, their chemical properties. And you can, lots of work has been done here with AGNs, black holes, host galaxies. And so I have mentioned here that HST has made significant contributors towards identifying intermediate to high-redshift galaxies, estimating their physical morphological properties, and understanding how they evolve with time. And so Hubble has been great, and it's going strong, but it's 31 years old now and has a limited lifetime. We hope that it continues for another 5-10 years, but you never know because it's already 31 years old. And the other thing is that HST is blind to the wavelengths further than near infrared. It cannot see the furthest galaxies, first stars, protogalaxies, and dense star-forming regions, which are usually covered by dust. And HST is not big enough to detect the faint light from first stars. It's a 2.4 meter telescope. It's a small telescope. And so we need something which is big and which can look into the near infrared, so we can look at the furthest we can see in the universe. And that's where the James Webb Space Telescope comes in. It's going to be launched on the 22nd December. And it's a 6.4 meter primary mirror, this golden mirror, the 6.4 meter. And JWST has 4 instruments, key instruments, NIRCam, NIRSPEC, NIRIS, MIRI, and they are the combination of imagers and spectrographs. And so they try to image the blank piece of sky, or with the spectrographs, you can resolve the wavelength into smaller chunks and try to get more details out of the galaxies. This near-infrared instruments need to be very cold, about -400, -450 Fahrenheit. And so that's why you see this large sun shield that is on the James Webb, which basically protects from the light from the sun going towards the instruments. And so the advantages of James Webb over Hubble, first is the primary mirror. Hubble is 2.4 meter, James Webb is 6.4. And so you have a light gathering power, which is much, much larger than HST or James Webb. And here you see the wavelength covered by HST, which is basically from ultraviolet to near infrared, while James Webb basically goes from near infrared to mid infrared. Spitzer was one telescope which was looking at infrared light, but it is a very small telescope, and so it cannot go very far as cannot look very far in the universe. And this is just the right plot is showing here how sensitive it is, and the red points for the James Webb shows that it can go much, much fainter than Hubble at these wavelengths, Spitzer, and other telescopes which have observed at this wavelengths. The other advantage is that compared to Hubble at near infrared wavelength, James Webb have a better resolution. And you can see more detail in this galaxy compared to this galaxy. And the sensitivity is much better, so it goes much deeper, much fainter. And so this is one of the Hubble Deep Fields. And if you do a James Webb Deep Field, this is a simulated image, you will see tons and tons of more galaxies compared to what Hubble can see. So size and sensitivity is a big advantage. And the second advantage is the infrared observation. As I mentioned, the redshifts, because the distant galaxies, which are at the beginning of the universe, they emit light in the ultraviolet. And if we want to see those lights, and we need to go into the infrared. And the Hubble didn't go to infrared, so Hubble has a limit that it cannot go further than that. While James Webb can probably look at the very first galaxies because of the near infrared sensitivity. And so here I have shown the electromagnetic spectrum again. Hubble looks in this spot, while James Webb is looking into this spot, the near infrared. So that's looking at the distant galaxies. The other aspect of infrared is that the dust. Now, visible and ultraviolet light, the Hubble observations, they cannot penetrate through this dust. So this is the same image of a same Carina Nebula. And you see this is the dusty part of the Carina Nebula, which is shown in visible light. But once you look in an infrared, you can see through, basically, you can see through these clouds. And the same here, this is a UV light, and this is the infrared light. And so what James Webb will enable is, it will be able to look through the dust, basically. And so all the dusty galaxies and you are not able to see with Hubble, you could be able to see through with James Webb. So size, sensitivity, and the wavelength are the three key aspects of James Webb, which gives a strong advantage over Hubble. So it is not a successor of Hubble, it's basically a complementary telescope. We actually want Hubble and James Webb to observe together for a few years, because Hubble observes in ultraviolet and visible, and the James Webb observes in near infrared. So if we want to look at the multi-wavelength aspects of the galaxies, then we really need both these telescopes working together. And so what James Webb will observe in first year. And so just to give an idea here, we have already selected programs for cycle 1, and about 10,000 hours have been allocated to the observations. Some guaranteed time observations, over 3,500 hours, director's times, which is early release, 500 hours, and then all the community general observer time is 6,000 hours. And so there are 400 individual programs, 2,500 investigators from all over the world, and nearly every area of astrophysics and planetary astronomy has been covered in the first year, because we need to show what James Webb can do in the beginning of the mission. And so just to quickly give you a glimpse of some of the programs, like one of this program has been approved, and it's looking at the nearby galaxies. Nearby galaxies, as I mentioned, are the great laboratories for understanding physical properties, because you can look through in detail of what's going on in the galaxies inside. And so about 40 galaxies, this program will look through near infrared and mid infrared observations with James Webb. It will look at the stellar populations. It will look at about 1,500 Cepheids. These are the stars which are basically the calibrators of the distance measurements to the nearby galaxies. So that will be very key. Look at the star forming regions, try to understand the interstellar medium, and we'll look at the spectroscopy of these galaxies, where you can do detailed chemistry. You can look at the chemical composition of the stars. As far as the first galaxies goes, one of the goals of the Webb is to look at the first galaxies, how they formed. And so there are programs which are looking at taking the advantage of infrared sensitivity and doing deep observations with NIRCam. Then Hubble, as I showed, has observed and identified many high redshift galaxies, redshift 8, 9, 10. And so there are programs which are looking to confirm these galaxies through spectroscopy, because with photometric redshifts, it's not accurate. And so you have some estimate of redshifts, but you don't know exactly where they are. And so there are programs looking at this. So one example is shown here of a redshift 11 galaxy identified in Hubble. And one of the goals of the programs, one of the approved programs, will be to confirm this galaxy. And in one case, the goal is to measure the metallicity of a single star. which is gravitationally magnified 9,000 times. Usually you see individual stars only in the close nearby galaxies. But here, because of the huge magnification that comes out of the gravitational lensing, that you are able to see individual star in the basically the early galaxies, and you can try to study what these first stars are basically. For the evolution of stars, evolution of galaxies, you can look at all the intermediate redshifts between redshift 1 and 6, try to understand the star formation, black hole growth, how the galaxies evolve. Multiple observations of the spectroscopy has been approved to look at the metallicities, the chemical compositions of the galaxies, AGN properties, and various other aspects of the galaxy, which we can now study in detail with James Webb. And so here, one of the simulated images shown how the galaxies will look like in the near-cam image of James Webb. And then there are programs which are just doing galaxy imaging surveys, like the one Hubble did. And this data set will be crucial to study galaxy assembly, try to study first galaxies as the Hubble done. And on the left, I have shown here some comparison. So you go from bright to faint. The yellow triangles are the Hubble programs, and the blue are the JWST programs. And you can see all the JWST programs are going fainter towards the right of the Hubble programs, and they're comparably in a pretty decent areas in the size. This is a small area sky, and this is a large area sky. So these are just the first year programs approved so far. So there will be much more coming in the coming cycles, coming years. With the spectroscopy, JWST will be confirming and studying basically thousands of galaxies at all redshifts. And some of the furthest galaxies, you will be able to see about 200, 300 galaxies with the James Webb spectroscopy. These are some of the programs approved, and these programs will observe these galaxies. And the significant part is that most of these surveys are public. So as soon as the observations are done, the whole community can use this data and try to do their own science with this. So it's great. And just to give a quick glimpse before I end the talk is one of the early release science program, SEERS, which has been approved. It's one of the 13 programs which will get the top priority as soon as the JWST is ready for science observations. And the goal of this early science programs is to demonstrate the capabilities of the James Webb Telescope, its instrument to do the various science that the people would like to do. And so from the early galaxies to all the galaxy assembly that has happened over the cosmic time. And so for this program, the proposers have used a small field in the sky, which has already been observed by Hubble. And then you're observing with different instruments of the JWST on the same patch of the sky and try to get more information out of it because of the JWST sensitivity and the wavelength coverage. And just to give you an idea here, this is the number density, and this is the redshifts or the distance of the galaxies. And these are the different models. The lines are different models, theoretical models. And this program will be able to differentiate these models depending on the 50, 60 galaxies that they will be able to observe in this small patch of the sky. And this is just a table showing how many galaxies they will be able to observe with the spectroscopy. So that's much more detailed. And on the right here, showing the comparison of the resolution, the details that you will get from the JWST. Now, this is the Spitzer image of a redshift 2 galaxy. And this is the simulated image of the JWST NIRCam. And you can see the substructure very clearly in this image. And you can do a detailed study of this galaxy compared to what you can do with this one. And similarly, in here also, this is an HST image on the left is a near infrared. This is a MIPS Spitzer image of 24 microns, and this is the James Webb simulated image. And you can see you can look much fainter with higher resolution than the Spitzer, and you will get much, much more details. I have mentioned here about a factor of 8 in the resolution and factor of 10 in the depth at all the redshifts you can observe for the galaxy evolution. And the last thing is one example of a redshift 9 galaxy observation. And you can see here HST observations on the top and the Spitzer current observations on the top also here. And this on the bottom panel is the JWST simulated images. And you can see clearly those is detected in all bands of JWST. And so here you're seeing the models here, 2 models. If you look at the red boxes, which are coming from the current data from HST and Spitzer, you will select the red model. But if you look at the JWST data, which is here the green boxes, and then you will choose a different model. So this detailed observations will be able to differentiate galaxies of different kinds and the models. And one last thing here is a spectroscopy here. As you can see, it can break down into individual lines, individual wavelengths. And this is an oxygen line, this is a hydrogen line, this is in carbon, this is again a hydrogen line. So you can, by looking at this spectrum, you can figure out the chemical composition of these galaxies. And this quality, this is a simulated one, but the quality of this spectrum is excellent because at present you can do this kind of quality for redshift 2 galaxies with Keck. But this is redshift 9 galaxies. So you're looking at very, very far galaxies with much, much better resolution. And to summarize, I would say that with HST and other ground-based observations, we have made significant progress towards understanding galaxies at high redshifts, basically all the way from nearby to redshift 6, with large samples in different environments. And we are not just counting galaxies now, we are trying to understand the physical properties of these galaxies. And we have done this with a multifaceted approach, looking at local galaxies, low redshift galaxies, lens galaxies, cluster galaxies, groups galaxies. And JWST will dramatically change our views on galaxy formation evolution. And we will have new discovery space. We'll get some unexpected results from JWST because of the very high sensitivity it is going compared to current facilities. So I would say thank you and go Webb.
Thank you so much, Nimish. Can we come, you can stop sharing, we can come back together as a group for some questions.
Definitely.
All right, everybody. Thank you so much again. Do we have any questions about galaxies? You have the expert here with you. I agree, George, it was absolutely fantastic. Thank you. Thank you. Any questions, you can raise your hand or you can put it in the chat box. I put in there because when I was looking up galaxies and you were talking about the mergers, Andromeda and Milky Way are due to merge in 4.5 billion years. So I don't think I'll be around to see that.
No. Yeah, so I think the main thing to take, because we are trying to understand galaxy evolution, and so we cannot follow one galaxy or 2 galaxies over their lifetime because it takes millions and billions of years. And so in galaxy evolution, what we are trying to do is we are trying to look at the different epochs or different times and try to study a number of galaxies and try to connect dots and see how they evolve.
So does that mean that we're one of when Andromeda and Milky Way merge, then that's just part of evolution? We're just becoming an older, more established galaxy.
Yeah, so we might end up as an elliptical galaxy, red elliptical galaxy after some time, yes.
Craig wants to know, do you look in any special direction to see farthest back in time?
No, we don't, but that's a very good question, because if you look at a one patch of the sky and try to do all kinds of studies, then we are biased in the sense that, because as I showed, that there's a lot of structure in the universe. It's not that uniform. And so we might be biased if we are just looking at one patch of the sky. And so we try to look at different fields, like as I mentioned, one of the Kendall's fields, where we, instead of trying to look at just one part of the sky, we chose 5 different fields in the sky. So 5 different regions in the sky. And so just we want to make sure that there is no bias going on, or there is no differences between this part of the sky and this part of the sky. And so, yes, we try to look as much as possible, but again, covering a large portion of the sky with a small field of view like Hubble, even JWST, the field of view will be comparatively very small. You cannot cover a large portion of the sky. And so we have to be very careful in choosing sky. So what we try to do, we'll do with JWST, is we'll first follow the fields we have observed with Hubble, because we know much more about those. And we have a lot of multi-wavelength data. And that's how we'll try to get more information. But yes, we try to cover as much sky as possible, but with small field of view like Hubble and James, it's very difficult to cover a lot of sky. For that, actually, the ground-based telescopes like the LSST, which is coming up in a year or two, and there will be large ELTs, extremely large telescopes. So they will cover a large portion of the skies, and they will do practically a survey type science. And so that will be a complementary thing to what Hubble and James is doing. James and Hubble telescopes are looking deep into a small portion of the skies, while this large ground-based telescope will not go that deep, but they will cover a large portion of the sky. So now you have 2 different perspectives to look at when you combine all those 2 things together.
George asks, do you have any hints as to what might be different from our current view of the universe to what Webb might discover?
Yes, as I mentioned at the end, what we are expecting from James Webb is to look at the earliest galaxies, try to refine our observations for the intermediate redshift galaxies that we have discovered with Hubble. We get more information because we're now looking at infrared. We are looking at much fainter because of the sensitivity of the James Webb. So those are the things we expect, because those are the things we have seen with Hubble, and we think the James Webb will be doing better on those things. But then there's a new discovery space. We don't know what James Webb will give us, in the sense that once you're looking so far into the universe, or very so close to the Big Bang or the early universe, that you don't know what to expect. And so there is that space of new discovery, which we never have thought about, which might come up with the James Webb. And I'm just here talking about the galaxies, but other fields also, like you're looking at the planetary science or stellar evolution. There are a lot of unknowns that just might come up with James Webb sensitivity because of it's just because of the large telescope, highly sensitive telescope. So no, I don't know what different things James Webb will bring us, but we're definitely looking forward to it.
That is the magic that we're all waiting for. I think in one of our former talks, it was a big gamble that they took to take that much time to put Hubble into one area, because that was the first time into deep space, and they were just amazed at what came out of it. They weren't expecting that. So that changed completely what we are understanding. So I know that James Webb will do the same, and we're all very, very excited to understand more about space.
Yes,
and how that
definitely.
Any other questions for Dr. Hathi tonight? Well, again, thank you so much for sharing your time, your knowledge, your expertise with us. We are smarter for it, and we can take this information and share it with others. We look forward to maybe having you back when James Webb is up and bringing back some data, and you can help us understand what it's seeing. And we look forward to spending more time with you, exercising our curiosity muscle and getting smarter together. So please join us for upcoming programs. Remember, Thursday is Spotted Lanternfly, but this Saturday, more space with the DIY planet search, and then more space in January with Europa, the Europa Clipper. So there's a lot of space out there. And December 22nd, mark it on your calendars. Tell everybody that you know James Webb is going to launch. Everybody, stay safe, stay well, stay curious, and we'll see you soon.
Thank you very much. Thank you, everybody.
Thank you.